Welcome to Efiwe, excellence without stress.
Hi guys, it's me, Miss Stella, your favorite physics tutor. And today on our journey into becoming a great scientist, into becoming a great physics student, and also into excelling without stress, we're going to take this our first topic, which is measurement. Measurement is very, very important in physics because it is actually the basics from which every other topic is actually built, because the understanding of measurement will help you when you start doing a lot of topic in physics. So today, this is our table of contents. We're going to understand what fundamental quantities and units mean, derived quantities and units. We're going to derive a lot. We're going to understand the basics. We are going to understand how fundamental quantities gives birth, or how fundamental quantities are used to get the derived quantities. We're going to go into dimension, and we're going to do how most of the quantities we have, like time, mass, are measured. We're going to go into scalar quantities and into vector quantities. So definitions. What are fundamental quantities? Fundamental quantities, the physical quantities which do not depend on any other physical quantities for their measurements, are known as fundamental quantities, or the base quantities. The best way to just define fundamental quantities is just to say, oh, these are quantities from which every other quantity are gotten from. It's just like the mother that gives birth to every other quantity. And just as the name implies, fundamental units are the units of the fundamental quantities. So what about derived quantities? What are derived quantities? These are quantities gotten from simple addition, product, ratio of two or more fundamental quantities. So it means that for you to get derived quantities, then you have to put two or more fundamental quantities together, and then you're going to get your derived quantities. And derived unit is just the unit of the derived quantity. So let's just check. These are the basic fundamental quantities we have. We have 7 of them. We have the mass. Let's start with length. Length, the unit of length is meter, and the symbol is m. So anytime you say m, it's talking about meter. Just like when you say your area is meter square. When you say length of something, it is a meter. Then the mass is measured in kilogram. That is, and the symbol is kg. Time, second, and the symbol is s. Electric current, ampere, and the symbol is a. Thermodynamic temperature, Kelvin, and the symbol is k. Amount of substance, mole, and the symbol is just MOL. Then luminous intensity, candela, and the symbol is CD. So all of these quantities are used to build the derived quantity. So in this our study, the major quantity we're going to focus on is the mass, the length, and the time. These 3 quantities are the major quantities from which most of other quantities are gotten from. So now let's check our derived quantity. We're going to work how we got these derived quantities. For example, now we have our area. Area is length times breadth. So length times breadth is m square. So what's fundamental quantity give birth to area? That's our our length. Our length gave birth to area. So going to volume is area times height. So area, we've already gotten that our area is m square. So when we multiply m square with another m, we are getting m cube. Then density, which is mass over volume. So let's just go to our board and try to derive most of this formula. So we want to do some topics on the derived. So the first one we're going to now, let's go to our density. So what is density? Density is actually mass over over volume. So it means now we're going to get this quantity, which is density. We're going to get the units, which is mass over volume. So don't forget that your mass is is in kg. Then your volume, which we got the other time, is m cube. So anytime you see divided by in physics, is called per. So we're going to have what is called kg per meter cube. So now the unit of density is kg per meter cube. So the fundamental quantity, which is mass, has given birth to another quantity, which is density. So density is a derived quantity. So let's go to another one, which is our speed. Our speed is distance over time. So here now we are going to use 2 fundamental quantities to derive our speed. So what is our distance? Our distance is measured in meter. So we're going to write our meter. Our time is measured in seconds. So it means speed was derived from 2 good fundamental quantities, which is meter and second. So we are going to have what is called meter per second. So this unit for speed is what? Meter per second. And we got it from our fundamental quantity. Let's do for velocity too. We have our velocity. Velocity is equals to what? Displacement over time. This is actually almost the same thing as our speed, because our speed is distance over time, but our velocity is displacement over time. Later on, we're going to know the difference between speed and velocity. The major thing is just that speed is a scalar quantity, velocity is a what? Vector quantity. So let's say displacement also is measured in what? In meter. Then time is also measured in second, which is also going to give us what? Meter per second. So you are seeing the way we are deriving quantities from the fundamental quantities. That's why you say fundamental quantities are the basic quantities from which what? Every other quantity are what? Are gotten from. So let's proceed. We're going to derive so many quantities today. So now let's go to another quantity. Let's go to force. Okay, let's go to acceleration before we go to force. Acceleration. So what is acceleration? Acceleration is velocity over time. Don't forget, in our previous, before I cleaned the board, we had we already derived velocity, and velocity was what? Meter per second. Then another time is what? Second. So this is just mathematics. Remember that when you have meter per second, that's what I'm saying, meter divided by second. Then we have another second again, so divided by what? Second. And don't forget your mathematical rule. I'm sure you did that. You know what I'm trying to talk about. So that's meter per second times 1 over s. And what would that give you? That is going to give you m over s squared. So definitely your acceleration is equals to what? Meter per second square. So are you seeing the way we are deriving a lot of quantity? I'm going to do some, and I'm going to give you the rest as what? Assignment. So let's go to another quantity, which is what? Our force. I'm taking it bit by bit because this is going to help us in deriving every other quantity. So let's go to force. So we have our force now. Our force is what? Mass times acceleration. So I won't be able to write that because of what is already on the board. So what is the unit for mass? I know you already know that. The unit for mass is kg, Abi, and the unit for acceleration, which we got here, was what? Meter per second square. So this is just multiplication. So automatically our force is what? Kg meter per second square. And it's as simple as that. So let's take the last one before we go to the next slide. So we have what is called the work done. Work done is equals to what? Force. Okay, let me write that so it won't be 2. That is equals to force times what? Our distance. And you know we've already gotten our force here, Abi. So kg, Abi, meter per second square times another distance. And you remember now distance is measured in what? In meter. So we have 1 meter here. We have another meter here. So taking the 2, it will be kg meter square per second square. And that's the unit for our what? That's the unit for our work done. So work done is kg meter square per second square. And don't forget, work done is also measured in what? In joules. Yes, just as force is also measured in what? In Newton. Our force is also measured in what? In Newton. So these are so important, like very important. So you've noticed the way we derived many quantities, and it's so simple. So let's take the last one, which is power. Power is equals to what? Work done over what? Over time. Don't forget how we got our work done. So let's quickly put that here, because I know some of you will be confused. Don't forget your work done was equals to what? Force, Abi, times distance. And you got your force as what? Kg, Abi, m slash s square times m, Abi, and it became kg m square slash what? S square. So putting these two into this equation, we're going to have kg, Abi, m square slash s square over another s. So what is that going to give us? So we have 2s already in the numerator. So now, taking the one that is in the denominator, we're going to have what? Kg, m square slash what? S cube. And that is the what? Unit for power. And power is also what? Is also watts. So, and that is all for our derived quantity. So let's go back. Oh. So now we've done a lot. We derived our area, we derived our volume, we derived our density, we derived velocity, we derived acceleration, we derived force, we derived okay, we did not derive pressure, but we derived power, we derived energy, and so on and so forth. So this is how to derive different quantity in physics. So from our fundamental quantities, which were length, mass, time, we derived our derived quantities, and it is as simple as that. So now we have something called the dimension. So the dimension of a physical quantity is defined as the power to which the fundamental quantities are raised to express the physical quantity. So very easily, when you look at this is just trying to put our physical quantity and giving them a kind of power that, okay, we have this amount of mass in this quantity, we have this amount of length in this quantity. Don't worry, you're going to understand. So for the dimension, length will be represented as L, mass will be represented as M, T will be represented as will be represented as capital T. So anytime we are solving anything on the dimension, instead of us to write, ideally the unit of length is meter. So but when we are solving anything on dimension, we're going to be representing length with the capital L. That does not mean that the unit of length is L. It's just trying to tell us, okay, in this quantity is density. Density is mass, over volume. How many M do we have? Okay, we have 1 M. So M will be raised to power what? 1. Do you understand? So how many volume do we have? It's going to be how many T do we have in this quantity? How many M do we have and how many L do we have? So don't worry, you're going to understand everything as we go back to our board. Let's go to our board and explain everything to you. So now, in the previous we derived so many quantities. So now, the first one we derived was what? We derived for area, right? So area was what? Meter square. Don't forget what I told you. I told you that for dimension, our L, our length, will be represented as capital L. Our mass will be represented as capital M. And our time will be represented as what? Capital T. So this is what we're going to use in this our dimension. So we have area is equals to M square. So what will be the dimension for area? The dimension for area will now be equals to what? L square. So when they ask you that, how many L do we have when it comes to area? So it's just as if how many L do we have? We have 2 in what? In area. So that is what dimension does. It tells you how many of this fundamental quantity, how many of this unit is in this quantity. So let's go to another one. Let's go to our density. So we have density. Don't forget, density is what? Mass over volume. Okay. So now, don't forget what we've talked about. Okay, let's do for volume first, so I will not get confused. Volume is equals to what? M cube, and which is also equals to what? L raised to power 3. So we have 3 L's in this quantity, but that is not telling you that the unit for volume is length. The unit for volume is meter cube. For mass, we're going to have what? The capital M, and for volume, we're going to have what? L what? Cube. So now, this can also be written as M per L cube. So we have how many M? 1, and we have minus 3 for the what? Length. Are we clear with that now? So this is what dimension does. So let's go for another quantity. Let's go to our velocity. You recall that our velocity was meter, per second. So writing this now, we're going to write our meter as what? Capital M, and our second as what? Capital T. Is that also? So this is the unit. So you can write it as M/, T. So it means you have 1 m and you have what? 1 t. Are we clear with that? So let's go to our acceleration. Just as we did for every other quantity, our acceleration is going to be what? Meter per second square. So our m is going to become what? Capital M. Then our L, our S is going to become what? T what? Square. And that can also be written as m/t square. Don't forget that this is a capital M. Are we good? So which other one should we derive? Let's derive for what? Force. Okay, let me clear the board so I will not get confused. So for our force is which is equals to what? Mass, right? Times acceleration. Our mass was what? Kg, abi? Ms minus 2, right? So when we have kg ms minus 2, so kg is going to turn to what? Let me rewrite the 3 dimensions. We already accepted that length will be what? Capital M, capital L, sorry. Okay, Control Z. Length will be what? Capital L, mass will be capital M, and time will be what? Capital T. So kg now, which is mass, will be represented with what? Capital M. Our M, which is for length, abi? Okay, let me just put this here. Don't forget that the unit for length is meter, the unit for mass is kg, the unit for time is second. So anytime we see M, we're going to be representing it with L. Anytime we see S, we're going to be representing it with T. And anytime we see kg, we're going to be representing it with M. So we have M here. So what are we representing our M with? We're going to represent it with what? L, capital L. We have S. What are we going to represent our S with? With capital T. Then we have what? Minus 2. And so here is the dimension. Let me write it down. M, L, T minus 2. So this is the dimension for force. So you see how easy, how simple it is. So let's take the last one, which is the dimension for work done. You see, I'm taking you through this process so you understand. This is very easy and very simple. So don't forget, your work done is what? Force times what? Distance. So having that at the front of your mind, you know your force is what? Kg, right? Ms minus 2. And you have your what? Distance also as m, right? So we have kg m square s minus 2. So getting the dimension is actually very simple, right? So we already said that wherever we see kg, we should just put our what? Capital M-O. Wherever we see m, we should put what? L. So we're putting L square. So wherever we see s, what are we putting? We're putting t, which is minus 2. So you see how easy this is. So what is the reason for knowing dimension? It's just for the scientists to just know, okay, in this quantity, how many m do we have? So if you were asked that, okay, how many m is in the quantity work done? You know that we have m equals to 1, abi? What about your L? Your L is 2. What about your T? Your T is minus 2. So this is why. It's just sorry, let me do Control Z so that it's not close. So for this quantity of what? Work done, we are able to know that m is 1 there. L is, we have 2L, that is length, right? And how many times? And this can easily be converted to the units, because once I just see m, I know that, oh, m, what they were trying to write, oh, was what? Kg, abi? And when I see L, I know that, oh, L, what they were writing was what? M square. And also when you see T, you know that T is what? S minus 2. So that is dimension for you. See how easy and simple it is. So let's continue. Let's continue. Oh God. So that is all about dimension. So I'm sure you understood everything we were talking about. And now, so this is a starter quiz, and I'm sure you'll be able to get everything. So which of the following are derived units? We have our meter, we have coulomb, we have kilogram, we have ampere, and we have joule. And you know that this should not be something that will be very, very difficult for you. I trust you. Your meter, is meter a derived unit? I'm sure you know that. Is coulomb, is it a derived unit? Is kilogram a derived unit? Is ampere a derived unit? So this is a quiz I expect you to be able to answer. So the dimension of power, did we do? Yes, we did it. You should be able to get the dimension of power from what I explained. You know, power is what? What's the formula for power? Power is work done over time taken. After using the unit of power, you can easily convert it to its dimension and choose the right answer. So they said, which of the following is a set of vectors? Oh, we've not really done vectors, but vectors are quantity that has magnitude and direction. Don't worry, you will understand everything, and you can go back to the quiz and answer. So they said, derive the dimensions for the following: momentum, mass over velocity. I trust you, my awesome students, that this is going to be very easy for you. Said the one for impulse, force times time, and power, work done. If you find anything difficult, you can as well reach back, and we're going to give you solutions to everything. So now this one is just so simple. So every quantity in physics has what we use to measure them. Every quantity in physics has different instruments of measurement. So this is length. You know, I told you physics is a precise science. We believe so much. We don't like cheating. No, we don't like cheating. So we don't like it. That's why we are so painstaking about what measurement. So this is length. So what do we use to measure length in the laboratory? What we use to measure length is called the meter rule. This is how it looks like. It is always long. And why is it called meter rule? Because it is 1 meter. And don't forget, 1 meter is equal to what? 100 centimeter. So also 1 meter is equal to 39.4 inches. But the basic one you need to know is 1 meter is 100 centimeter. So that's the length. It is measured using a meter stick, or you call it a meter rule. Yeah, it is long. It's just like your ruler, but longer than it, because it is in meter or in centimeter. So that is for the length measurement. So let's go to the mass. Mass, Abby. The mass of an object is the quantity of material it contains. That is what mass is. So mass is just as if I open the bag and I put so much things inside. So whatever that thing contains is what is called the mass. So it is measured on a balance. So this is what we use to measure what our mass. It's called a being balance. We can have a chemical or being balance to measure our mass. So the unit is in gram or in kilogram. Don't forget, you know that your gram and kilogram, they are the same. It's just that we have 1,000 gram in 1 kilogram. So that is just, so the SI unit of mass is what? Kilogram. What do you should know the meaning of System International of Units. These are units that are generally accepted. It means that if I want to, if in Nigeria now I measured my weight as 15 centimeter, the fact that you want to send the measurement to someone in America does not mean that you have to add 100, because you know, before you get to America there is a long distance. No, it is accepted. Our kg in Nigeria is the same kg abroad. Our centimeter, our meter in Nigeria is also the same meter in America, in Czechoslovakia, and so on and so forth. So we go to time measurement. So what do we use to measure time in the laboratory? We use what we call either the stop clock or the stopwatch. And see it now. So later on, I'm sure you are going to understand how to use this awesome apparatus in the laboratory. So that's for the time and the temperature. The temperature of a substance. So this is what we use in the laboratory. We use what is called the thermometer. All these are still going to be taught in are going to be taught more in other classes. So for the volume measurement, use the cubic meter. For the volume measurement, you use a measuring cylinder. Use a measuring cylinder, or called a graduated cylinder, to measure the volume. But if it's an irregular volume, there is a way we measure an irregular volume using the Eureka can. What you do is you're going to fill the Eureka can with water, and then you're going to throw the irregular solid into. What is an irregular solid? An irregular solid is a solid that you cannot even say the shape. Maybe it's circle, maybe it's square, maybe it's anything, like just like your stone. You know, you can't really depict the size, the shape of a stone. So when you throw it inside, whatever liquid is displaced is the volume of that irregular solid. So now we are going to this vernier caliper and the micrometer screw gauge. You see, the meter rule is used to measure anything that is actually totally straight. But physics, we are not thinking about periods where we have a test tube. How can we measure the diameter of a test tube? So that is when we have these awesome instruments were discovered, which is the vernier caliper and the micrometer screw gauge. So look at this micrometer screw gauge now. This place is where you're going to put whatever it is you want to measure. The beauty of micrometer screw gauge, it can measure very thin anything, like the thickness of a sheet of paper. The micrometer screw gauge can measure it. So this one can measure the diameter of a small bulb. You just put it here, you put it here too, and you'll be able to measure the diameter. Just imagine this micro. Micro means very small. So if you want to measure the thickness of a sheet of paper, just put it here, then tighten this place. You close it up from here and it will tighten it. But this one cannot be used because it can't close more than a particular distance. So this one can only measure the diameter of a small ball. So this is the vernier caliper and the micrometer screw. I'm going to explain how to read the vernier caliper and the micrometer screw gauge, because they have two readings. They have what is called the vernier reading, vernier scale, and the main scale. So the addition of the vernier scale and the main scale is what is going to give you the reading of that, whatever it is you want to measure. And don't worry, I'm going to get it. So he said a vernier caliper is used to measure external measurements. The minimum count of vernier caliper is 0.01 centimeter. So let's just quickly go through the differences. Vernier caliper and the micrometer scale, it is used to measure internal dimensions. This micrometer, this vernier caliper can be used to measure internal and external, because this small thing can enter a small a small tube or any tube. If you want to measure the internal diameter of that tube, you can put this inside, but this cannot be used to measure anything internal. It can only be used to measure external things. So it is used to measure internal dimensions. Micrometer cannot be used to measure internal dimensions. So its least count is 0.1 meter. The least count is 0.01 meter because it's micro. It is smaller than the vernier caliper and so more. So it is more precise. Why is it more precise? Because it takes very small measurements. So the precision is better than the vernier caliper. So let's go to the next slide. So now we're going to explain how to take this reading. So this is two different this one is the vernier caliper and this one is the micrometer screw. How do we take the reading? The first thing you need to understand is this upper part is called the main scale, this lower part is called the vernier scale, and also for the micrometer screw gauge, this part is called the main scale and this part is called the vernier scale. So let's check our readings now. So how do I know the reading of the main scale? So it's so simple. Anywhere you see this line, that is the line where the vernier scale is starting, wherever that line starts from, that is where the main scale stops. Please don't be confused. Just check this vernier scale line. Wherever it is, it stops. That is exactly where the main scale reading stops. So let's check. This is 1. So automatically this is what? 0, 0.1, 0.2, 0.3, 0.4, 0.5. So our vernier scale is what? 0.5. So our main scale rather is 0.5. So now how can we discover, or how can we determine our vernier scale reading? Our vernier scale is so simple. Anywhere there is a this thing where the main scale and the vernier scale meets, at that point you're going to look as if you are seeing just one. You know, now there are different calibrations there, but at that point the main scale and the vernier scale will look as if it's the same thing. There is no difference between the two of them, and that's what's going to give us our vernier scale. So let's check now. What points do we have it that the upper part, that is the vernier scale, and the main scale look as if they are one? So this is the point we have, and that is what? 0.03. At that point, the vernier scale and the main scale are the same. So 0.03. So when we add 0.5 and 0.03 together, we have what? 0.53 centimeter. So this is the reading for this vernier caliper. So the same thing goes to the micrometer screw gauge. For the micrometer screw gauge, it's different. So this one here is the vernier scale, is the main scale rather, and this is the the vernier scale. So how do we take it? Is in 0.5. So this is 0, 0.5, 1, 0.5, 2, but you don't have any issue. Just go to the last one because this is 5. So 5.5, but you can just say 5, 6, 7. So that's the main scale. So the main scale is what? 7.00 millimeter. So let's go to the other one, which is the vernier scale. How do we know the vernier scale? Just the same way we said, wherever the upper calibration for the main scale and the lower calibration for the vernier scale meets, that is going to give us the vernier scale. So the same thing, this line, middle line for the main scale and this calibration, wherever you see them meeting, that's the reading for the vernier scale. So let's take that. You don't need to start reading from the lower part. So this is 30 abi, and you see this is 35. So this is 31, 32, 33, and so that is 0.03. So you might be wondering, why did I divide this one? You have to divide it by 100 to give you the calibration, because it's in millimeter. So you have to say, if this is 2, you have to divide it by 100. So that's why I add 0.03 here. So but this one, there is no need for that. It's already in millimeter. So the vernier scale here is what? 0.33. So when you add the two together, you're going to have 7.33 millimeter. You see how easy it is? No issue, no problem. So let's go to the next slide. And this is your assignment. Very simple. I'm going to quickly put you through. So look at it now. For this very first one, you remember that it means that your main scale is what? 1.00. So what is going to be your vernier scale? So the point where the upper calibration and the lower calibration meets, just count it one by one. So this is 1. Okay, this one is so simple. I think that should be the, I won't tell you, but check. You add them together, you add the region of the main scale, the region of the vernier scale together to give you what? Your vernier caliper reading. Then same thing goes here and here and here, and you are good to go. So very quickly, this is one of the questions that you saw in your starter quiz, so which is scalar and vector quantities. What are scalar quantities? What are vector quantities? So scalar quantities has only magnitude. So when you talk about magnitude, you're talking about size. As I'll just say, this thing is this big, no direction. And why vector quantity has magnitude and direction? I'm just going to use distance to quickly describe that to you. For example, now maybe you want to go somewhere. You just said, I'm going 10 kilometer. You've only given us our size. 10 kilometer could be to the north, it could be to the south, it could be to the east, and it could be to the west. But we don't know. That's what scalar quantity does. It only gives us what? The magnitude. But when you talk about the vector quantity has what? Magnitude and direction. That is, it will give you both the size and also tell you, in this particular direction. For example, I'll tell you that I'm going 10 kilometers in the northeast direction. So that is a specified direction. What are the examples? We have distance. Y for vector is what? Displacement, and so on and so forth. So go through it and understand the difference. Thank you, and this is the end of the class. Please don't stop here. Go through all the slides and understand everything. If there's any difficulty you're finding, you can always reach out to us. Thank you.